Panspermia hypothesis suggests that life, or its precursors, may have arrived on Earth from other celestial bodies, such as Mars. Geological evidence from rovers like Curiosity and Perseverance indicates that Mars had potentially habitable surface conditions between 4.1 and 3.0 to 3.5 billion years ago. This was the period when life could have emerged on Mars, with liquid water, lakes, and possibly oceans. Earth was also habitable very early on, with isotopic evidence suggesting life existed as far back as 4.1 billion years ago, and unequivocal fossils dating to 3.5 billion years ago. However, the Late Heavy Bombardment between 4.1 and 3.8 billion years ago repeatedly sterilized both planetary surfaces. This period created an extremely hostile environment for any emerging or transferred life. For Martian panspermia to be relevant, life would have had to arise on Mars before it did on Earth and be transferred here before independent life emerged on our planet. The early habitability windows of Mars and Earth overlap, but the LHB greatly complicates the picture. There is no evidence to suggest that life arose on Mars significantly earlier than on Earth. In fact, conditions on early Earth, such as greater mass and plate tectonics, might have been more favorable. Transfer during the LHB was hellish. An impact big enough to eject Martian rocks would probably sterilize the source region. Could transferred life survive this hell at both ends? After 3.8 billion years ago, Mars quickly lost its atmosphere and surface water, becoming less habitable. The window for ejecting viable life from a superficially habitable Mars to an already habitable Earth is very narrow. The lack of direct evidence is the Achilles heel of Martian panspermia. Hundreds of Martian meteorites have been identified on Earth, intensely studied for signs of life. The ALH 84001 meteorite sparked controversy over possible microfossils, but the current scientific consensus is that all the features have abiotic explanations. No other Martian meteorite has provided conclusive evidence of past or present life. The Viking missions in the 70s produced ambiguous results, interpreted as abiotic chemical reactions in the Martian soil. Modern rovers, like Curiosity and Perseverance, have found clear evidence of past habitable environments and complex organic molecules, but so far, no unmistakable sign of past or present life. Perseverance is collecting samples for more in-depth analysis back on Earth. If life on Earth came from Mars, wouldn't we expect to find some distinctive biochemical or genetic signature? The tree of terrestrial life points to a last universal common ancestor, well adapted to early Earth conditions. Local panspermia doesn't solve the problem of the origin of life, it just moves it to another planet. The likelihood that all the stages of transfer would happen sequentially and successfully is still low. Given the lack of positive evidence, the most parsimonious hypothesis is that life arose independently on Earth. Physical challenges, such as cosmic radiation and thermal sterilization, pose severe barriers to microbial survival. The critical time window for a viable transfer is extremely narrow and speculative. The complete absence of direct evidence, despite decades of study, is its greatest weakness. Mars shows a habitable past, but there is no evidence that it actually harbored life. Local panspermia lacks solid empirical support and faces substantial obstacles. An alternative version, molecular panspermia, proposes that the building blocks of life were delivered to early Earth. This hypothesis has concrete evidence, such as the Murchison meteorite, which contains complex organic molecules. However, heating during atmospheric entry and terrestrial contamination can degrade these molecules. The concentrations of these molecules in meteorites are very low, and many are not biologically relevant to terrestrial life. The sudden shock and high pressures during impact could degrade fragile molecules, even in the core of the meteorite. Even if they survived intact, they would be diluted in the vast primordial oceans, making their local concentration insignificant. The greatest mystery of abiogenesis is not the synthesis of simple organic molecules, but the steps toward complexity. This includes the formation of functional polymers, the origin of specific catalysis, and compartmentalization. Molecular panspermia doesn't address these fundamental problems. It only provides another source of raw material. The evidence from meteorites is irrefutable. Abiotic synthesis of organic molecules occurs in space. However, the quantity and biological relevance of the delivered compounds is questionable. Molecular panspermia does not address the crucial steps of abiogenesis. Its relative contribution compared to terrestrial sources declined rapidly after the period of heavy early bombardment. Therefore, although molecular panspermia may have contributed to the primordial soup, it does not solve the central problem of abiogenesis.